Hello, I'm John Davis and I've been thinking about the horizon problem. Now, this is a problem that came up in the 1960s when the cosmic microwave background radiation was first discovered. It was first thought to be a low-level rumble caused by some local activity, but it was turned out to be anywhere and everywhere and the same value all over the place. So it was put up. This is my illustration of cosmic microwave background radiation. If we look in one direction, we can see the radiation that's coming from 14 billion light years away, and if we look in the opposite direction, we can see the radiation that's coming from 14 billion light years away, and it's in every direction, there, and there, all over. It's been studied extensively, and it's been discovered that it's virtually identical in nature from all directions, which means that at some time in the past it must have been in communication with each other. Now, all of those parts must have been in communication with each other. And the problem is that the universe is thought to be only 14 billion years old. 13.8, but let's keep it to easy numbers. 14 billion years old, and light has only had time to travel 14 billion light years. But this point here and this point here are said to be 28 billion light years apart, so they have not had time to make any communication. That, in essence, is the horizon problem. Now, we can think about this in all sorts of ways, but I got to think that if we think about light, and I thought, what do you do if you add two speeds that together would normally come to more than the speed of light, which can't happen, as we know. If we've got two speeds, everyday speeds, we simply add them. If someone is walking in a railway carriage, the railway carriage is moving at 60 miles an hour, and this person is walking along it in a forward direction at 5 miles an hour, then an observer could, on this embankment, could simply say the walker is moving at 65 miles an hour. But what happens if the two speeds we're considering add up to more than one c? Well, there is an answer which I'll come to. I'll start with it now. Einstein pointed the way for this. He didn't develop this one, but he did say this is the way we should be doing it, and it's the Lorentz transformation. I'm not going to go through all the details here. This is up here. If you want to take it down, you can, but it is simply that the resultant velocity of adding v1 and v2. v1 is the speed that these two bodies are moving apart at, and v2 is the speed that these two bodies are moving apart at. The resultant speed of these two bodies moving away from each other is, in normal circumstances, it would be v1 plus v2 divided by 1. But as v1 and v2 come closer to being comparable to c, we have to add this last part in, which is v1 times v2 over c squared. So that's the Lorentz transformation. Now, if we think of a time after the Big Bang, but long ago, when space was there, the plasma had sorted itself out, and we were getting bodies moving around. If we now just imagine a line of inertial bodies, all in a straight line, all the same distance apart, d, and all with the same increasing velocity, v, between neighbouring bodies, okay? Because they're inertial, which means there is no acceleration, they're not accelerating, which also means they are not rotating, then each one of them is as good as any of the others to be used as a frame of reference to take our observations from. Now, let's just consider three in the line, these three, and say, right, the two, so that the three bodies are moving apart like that. Now, if I choose a v, they're the same velocity and the same distances because they all started supposedly at the same point. So this is a la Big Bang. If we choose v to be more than half of c, so that the two v's come to more than c, what do we get? Well, if we suppose that, I'm just looking for the right one, here we are. If we, so just something more than half of c, but obviously less than c, well, 3c over 4, 3/4 of the speed of light. If we have these two speeds here, the resultant speed, you can work it out yourself. It's not difficult. We're using the Lorentz transformation. It comes out to 24c over 25. Or to put it another way, it is 1/25 of c less than c. Now that's pretty good so far. But what now? Looking for the right. What now if we consider out of this original line, we consider a B4 here as viewed from B1. Okay, and here we've got it B1. There's B2 has just been faded out. B3. Now we've got 3c over 4 is the speed that these two are moving at with respect to each other, and 24c over 25 is the speed that these two are moving away from each other with respect to each other. Again, if you push these two numbers into the Lorentz transformation, you'll come up with v, the speed between B1 and B4, as 174c over 175. Or, to put it another way, it's 1 part in 175 less than c. It's getting close to looking like c. We can do this again and again and again. We've got an infinite number of bodies that we can choose to use. Just out of interest, the next one along, the fifth one, it turns out to be 1 part in 1201 away from c. So there will come a point when, as far as an observer on B1 is concerned, no matter how sophisticated their equipment and how many times they do it and how many different ways they measure the speed of this body, which I'm calling c for the speed of light, there'll be a body, BC, that appears to be going at the speed of light, even though it's not. It appears to be going at the speed of light, and there's still more going on beyond that. If we now considered an observer on BC looking backwards this way, of course, they will look at all these bodies and note they seem to be going faster and faster and closer to the speed of light until this one actually seems to be going at the speed of light. What's going on? Well, 1 second. BC, the observer on BC, is just as justified in looking the other direction to find that at this infinite line of bodies, there's one there that is the nearest one that appears to be travelling away at the speed of light, and all the others beyond also seem to be travelling at the speed of light. So now we've got an observer here saying something here is moving away at the speed of light, and something here is moving away at the speed of light. And if they've been doing it for 14 billion years, this one is 14 billion light years away from here, and this one is 14 billion light years away from here. But they all started in the same place, at the same time, at less than the speed of light. Does this sound like the horizon problem? It sounds to me like this is the mechanism that can explain the horizon problem. What's going on? Well, we sometimes hear, if we receive an unwelcome message, we are urged not to shoot the messenger. In other words, don't blame the person or the agency that brought you the information you didn't want to hear, but address the information. Well, I'm afraid it's the opposite with light. We've seen we can have as many bodies as we like moving away from each other, an infinite number of bodies. There's 1 billion galaxies out there, and each one's got 1 billion stars in, so we can easily choose as many of these bodies as we like to be moving away at any speed. It needn't be 3c over 4, it could be any speed you like, but the lower the speed, the more of these Lorentz transformations you've got to go through before you get to that one, the BC, the one that seems to be going at the speed of light as observed by the observer on body 1. Whenever we observe anything in space, we have only one medium through which we can get the information, and that's light. But light doesn't always tell us the truth. As an example, let's consider our 3 familiar bodies, B1, B2, B3, and put an observer on B2, and the observer is looking at B3 and B1. Now, a light year is the distance that light travels in 1 year, and a light second is the distance light travels in 1 second, which, as we know, is 300,000 kilometres, or 300 million metres. Now, going with our speeds here, we've got the speeds of 3/4 of the speed of light between those two. During the course of 1 second, the observer on B2 will note that B1 has increased its distance by 3/4 of a light second. And similarly, the observer on B2 will have noted that the distance to B3 has increased by 3/4 of a light second. Therefore, the distance between B1 and B3, according to B2, got that, is 3/4 plus 3/4, which is 1.5 light seconds. It follows from that the observer on B2 will say that the speed between B1 and B3 is actually 1.5 times c. There's a discrepancy here, isn't there? And the discrepancy, I believe, is that it is impossible to detect a speed greater than light, that of light, but it is possible to deduce a speed, any speed at all. Light isn't telling the truth always. And how can we be sure of this? Well, here's another thought experiment that I think will show it. If we imagine now our 3 bodies, but not in a straight line, but in a corner of a square like this, again increasing the speed between each of them as before. But one of the strange phenomena of the relativity is that a moving object suffers a contraction in its size in the direction of motion. So, an observer on B1 would notice that B2 has shrunk in this direction of motion. It's not as big in the direction of motion as it was when it was motionless. The strange thing is now that if we look at an observer on B3, they will observe that B2 has shrunk, but in a different way. Now, B1 and B3 have equal authority as frames of reference, and therefore neither has authority or preference over the other one. And since they can't both be right, they must both be wrong. And so it's another case of the light not telling us the truth. Now, in conclusion, then, our understanding of the horizon process arises from our conflation of these two ideas. One is the observable speed of anything, and the deducible speed of anything. Once we've separated these two phenomena, the horizon problem no longer presents any difficulty. I would just like to, I hope that this little chat has given you something to think about. I have just noticed that I'd forgotten to put the T in Lorentz earlier on in the video, so thank you for that. Thank you for your patience.